Let's take a look now at section 15.3 and talk about line integrals in conservative vector fields. Now, I mentioned previously that the language of conservative vector fields and potential functions and so forth is suggestive. It's meant to suggest something physical about these properties, about the properties of these mathematical objects. So here, let's take a look at what we mean when we say conservative. Well, we know what conservative means. We know it means that it's a conservative vector field because it's the gradient of some function. Well, now let's explore that physically. What does that mean? All right, so let's consider two physical examples. Note the following vector field. All right, and let's welcome our cyclist friends here, Callum and Roy. All right, so now they're going to start at a common place here, and they're going to bike over this way. Now, note that given this vector field, here you can imagine a wind that is, I'm not sure why they're biking in a tornado, but it's going around in circles. Notice that it makes a tremendous difference what path they take. If one of these cyclists goes this way, they have a headwind. They have a wind directly in their face the entire path. They then turn and travel this way, and again, they have wind against them the entire time. This would be the worst way to go, right? You would be facing the wind every step of the way, making it very difficult to traverse anything. Now, on the other hand, if this person went to the exact same spot going the other way, well, here they would be traveling with the wind, and then they would turn with the wind as well. Notice that here, even though they both traveled from the same starting point to the same ending point, they had a very different experience. One faced a struggle all the way, meanwhile the other one essentially could coast all the way. If you then took a different path, you might say, well, what if I went straight along here? Well, then that would be a totally different experience. Because notice as I'm traveling here, the wind is not really with me, because it's not at my back, it's not pushing me, but it's not really against me either, because it's not coming toward me, at least not directly. Here, it looks like I have someone coming at me from the side and moving away from me from the side. So traveling this way would give me yet a different experience. So here, I am traveling from one point to another in a vector field, and the path that I take gives me a very different experience. Now, consider a different vector field, something that looks like this. I could have something that looks like this and have a similar question. What happens is I go from here to here? Well, let's see. If I travel this way, I have a lot of wind that's coming across my side, so it's not really helping me. But then when I turn, I'm going to travel with the wind. So here I have a neutral experience, and here things are good. All right, well, now maybe I want to go this way. Okay, well, if I go this way, again, I have a neutral experience as I'm traveling here. The wind is at my side. But then when I turn, now things are easier. Notice that even though these took different paths, this had the same experience as this path. All right, this gave the same experience. You have something which is not really helping, but not really hurting. It's a neutral experience, followed by a whole lot of speed going off in that direction. Note that if I travel along this direction, if I say I'm going to go just straight along, I have a wind at my back the entire time, but it may not be as strong as it was over here. Here it is head on, or rather directly at my back, whereas over here it may only be at a bit of an angle. So depending on the path that I take over here, I will have a very different experience. However, depending on the path that I take here, well, actually it doesn't depend on the path. Regardless of which path I choose, I seem to have a similar experience. Now, well, what if I did this? What if I did a very unusual kind of winding path? Would that make a difference? Well, it turns out that if this vector field is set up just correctly, no, that won't matter either. You could take the most direct path, you could take a circuitous path, or you could take a very winding path that was completely inefficient, and from a point of view of how much work was done, these are identical. All right? So obviously I have different experiences depending on the path that I take, and that depends entirely on the kind of vector field that I'm in. I think you may see where I'm going with this. When we call this a conservative vector field, the thing that it conserves is the amount of work done independent of path. That brings us to the central theorem, not just of this section, but sort of this course. You see the fundamental theorem of calculus in Cal 1, which tells you that if you want to take the integral of a function, the definite integral from a to b, what you can do is you can find the antiderivative, evaluate that antiderivative at a, evaluate that antiderivative at b, and then subtract. The fundamental theorem of line integrals says something similar. So we begin with an open region R. Here, we're going to define this as if it were on 2 variables, but this will work for 3 or 4 variables as well. So for now, we're going to talk about this region as if it were a plane region, but it can be in any number of dimensions. It can be in R3 or otherwise. So let R be an open region. Let C be a piecewise smooth curve in R. When you say piecewise smooth, that means it doesn't have to be totally smooth, as long as you could break it into 2 or 3 or 4 pieces that were smooth. Something like this. All right, this is smooth, smooth, and smooth, even though right here we do have a cusp. So it's not smooth all the way, but it's smooth for several pieces. You could cut it into pieces that were smooth. Okay? So let C be a piecewise smooth curve in that open region R. We're going to define that piecewise smooth curve the way we have been, as a vector-valued function, where the first component is x of t, and the second component is y of t. And t is going to be bound so that we have a finite length to our curve. We don't want this to go on forever, so this is going to start at a and end at b. Okay? So we have an open region and a piecewise smooth curve defined by a vector-valued function. Now, let's let f of x comma y be given by m comma n. Let's let that be a vector field, but in particular, we want this to be a conservative vector field in the region R, where m and n are continuous in the region R. And since it is a conservative vector field, then that means that it is equal to the gradient of some function. So whatever this vector field is, we know which function has a gradient equal to that vector field. Okay? We know the potential function. In fact, let's label that. Here, f is our potential function. Okay? If all of that's true, if you have R as an open region, C is a piecewise smooth curve defined as a vector-valued function, and f as a conservative vector field, which has little f as its potential function, then the line integral over C of f dot dr, the line integral of that vector field over that contour, over that line, is equal to the gradient of f dot dr. Okay, well, that's just a simple substitution. After all, the vector field is the gradient of f. The vector field is the gradient of f. So here, that's just a substitution of notation. But this part is the desired result, and that is that this line integral, whichever way you want to represent it, is equal to the potential function evaluated at the at the endpoint minus the potential function evaluated at the initial point. Or in other words, it's about as close as we can get to the fundamental theorem of calculus while still having a parameterization of a function and while still dealing with a vector field. What this says is the line integral is equal to the potential function evaluated at b minus the potential function evaluated at a. But remember, the way we found a potential function was by taking the antiderivatives with respect to x and y of the components. So in a way, you could paraphrase this as saying the integral is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Or in other words, we're repeating the fundamental theorem of calculus. The proof of this is really very short, mostly because the proof of this relies on the fundamental theorem. Here, all we need to do is rewrite this in a more accessible form, and then the fundamental theorem of calculus takes over. So here, let's start off with this side here. let's take the line integral of our vector field over our contour over our line, so integral over c of f dot dr. We have seen in a previous section that this can be written with a parameterization as the integral from a to b of f of, well, here, let me write this as just f. This is, a function of x and y, a vector valued function. But here we'll write this as just f dot dr dt dt. And again, that's just, we've written this as our parameterization. We've written it using a parameterization with respect to t. So now it's a single integral with respect to t. And here dr, well, we're just using the chain rule. Since r is a function of t, then dr is really just the derivative of r dt. And that's just the chain rule. Okay, but now we know that this is equal to the gradient of some little f, right? Given these conditions, we know that f dot dr dt dt is really the gradient of f dot dr dt dt, like that. But we know what the gradient looks like. We know that the gradient is equal to f sub x comma f sub y. Here I'm proving this the way it's written for two variables. Of course, this can be done for any number of variables. And here I can go ahead and write this as dx dt comma dy dt. Because after all, that's the derivative of r with respect to t. If I take the derivative of r, that's the derivative of the first part, which is the derivative of x with respect to t. And then the derivative of the second part would be the derivative of y with respect to t, dt, which we can now write as the integral from a to b of the way the product rule works. It's the product rule. The way the dot product works, that's going to be f sub x dx dt plus f sub y dy dt. Right, this times this plus this times that, dt. But if you notice now, the partial of derivative with respect to x times dx dt, that's just the derivative of your first component with respect to t. Likewise, the partial of y of f with respect to y dy dt, that's the derivative of our second component of f with respect to t. Or in other words, we're using the chain rule. Here, that's the derivative of the function times the derivative of the variable. Right? Here's a function of x and y. Okay, well, we only want to treat y as a variable, so we're going to take its derivative with respect to y. And now we're multiplying that times the derivative of that function, that y, with respect to t. Well, that's just the derivative of the outer part of the function times the derivative of the inner part of the function. That's the chain rule. And here I'm applying the chain rule to both variable functions of my vector field, which means I can write this as the integral from a to b of the derivative with respect to t of each of these, which, let's see, how do we want to write that? I mean, really, it's just one function with two variables. So we should write this as the derivative with respect to t of f of x of t comma y of t. And this was the chain rule that we saw back in chapter 13 point something. Right? Here, if I were to take the derivative of f with respect to t, I would take the derivative of f first with respect to x. But then I need to take the derivative of x. And then I would take the partial with respect to y. But then I need to take the derivative of y. And then I would add those together. That's what this is. So this, in parentheses, is really just the derivative with respect to t of this function, dt. But now that's just a regular function. And now by the fundamental theorem of calculus, if I take the antiderivative of a derivative of a function, well, that just gives me that function again, doesn't it? But I have the function evaluated at endpoints. Okay, so that's going to be f at, I'm plugging in t is equal to b. Okay, so those become b. So f of x of b comma y of b minus, and again, the antiderivative of the derivative of my function, that's going to be f of x at a, y at a. And that is strictly just the fundamental theorem of calculus. Right? The derivative of the the integral of the derivative is just going to be the original function. And since it's evaluated at endpoints, once we have that antiderivative, which is just our original function, we're evaluating it at our endpoints, at b and at a. And that concludes our proof. That's exactly what we wanted. Right there. So this confirms for us that as long as you have a conservative vector field, and as long as you have a curve that's piecewise smooth in some region of that vector field, taking the line integral doesn't depend on the line. It only depends on the potential function and on the beginning and end points of my curve. So as long as my vector field is conservative, it doesn't matter if I start from here and end here by this path, or anywhere else in between. By the time I'm done, it'll only depend on the potential function, which will be true for the entire vector field, the beginning point and the end point. It'll be completely independent of the path. This leads us to some very nice examples. Let's evaluate the following integral. Evaluate the integral over the line C of x squared plus y squared dx plus 2xy dy. So here we have a line integral over a vector field here, right? We have a line integral in a vector field where it's given in its differential form. Okay, so first of all, we need to confirm that we are in our conditions here. Oh, and I have a contour given here, where C is given by R of t is equal to t to the third comma t squared, and t is bound between 0 and 2. Okay, so here we're going to say, okay, first of all, we need to make sure we have our conditions. The fundamental theorem of line integrals doesn't work for every line integral. It works for some with specific conditions. All right, let R be an open region. Well, we're in the plane, so that's definitely an open region. Let C be piecewise smooth curve in R. Well, sure. In fact, here, this is defined by the x variable is smooth, the y variable is smooth. By smooth, I mean it has both derivatives. Right? And so here, this is going to be polynomial. The components are going to be polynomial. If you really want to convince yourself, you can always remove the parameter. X is equal to this, y is equal to that, and you could write this as a, what would that be? Y is equal to t squared. So you could write this as square root of y is equal to t. You could write this as cube root of x is equal to t. And so cube root of x is equal to the square root of y. Or in other words, y is equal to x to the 2/3 power, which is definitely a smooth function. Right? So here you can convince yourself any way you like of that, but here the simplest way is to say, oh, these are both smooth. So it's a piecewise smooth function, and m and n are continuous in R. So here these are not going to be difficult to confirm. We have an open region, sure, we're in the plane. And here this is definitely piecewise smooth because these are smooth, right, and continuous. Everything works out nicely. The thing we really want to watch out for is this third condition. We want to make sure that f is conservative. All right? If it's not conservative, you cannot apply this, which means if this is not a conservative vector field, we can't use this theorem. We actually have to go back and do what we were doing in previous sections where we would substitute, x is equal to t to the third, y is equal to t squared, dx would be 3t squared dt, and dy would be 2t dt. All right? If this was not conservative, then we'd have to do it that way. So first of all, if we're going to use this theorem, we need to check if this is conservative. Fortunately, there's an easy check for that. Let's go ahead and find the partial of n with respect to x. Now remember here, when written in its differential form, this is your m and this is your n. So when we say del n del x, we mean the derivative with respect to x of 2xy, which is just going to be 2y. Okay? And then we also need to find del m del x, but since that's m, what we really want is the partial with respect to, that should be a y right there, shouldn't it? The partial with respect to y of x squared plus y squared. And here the derivative of this would be 0, and the derivative of this would be 2y. So here these match, which means that your vector field is conservative. All right, so now that we know it's conservative, all we need to do is find its potential function. Okay, so let's go ahead and do that. Finding the potential function. When your vector field is written in its differential form, it practically just gives you the answer. Because look, right here, if you're looking for the potential function, what you want to do is you want to take the integral of m with respect to x, and you want to take the integral of n with respect to y. Notice basically you're just trying to evaluate this integral, and you're trying to evaluate this integral. So let's go and do both of those on their own. Here we're going to take the integral of x squared plus y squared dx. And let's see what that is. With respect to x, that's going to give us x to the third over 3. And with respect to x, that's just going to be xy squared. Now let's find the integral with respect to y of 2xy. Again, we're just doing both of these. We're doing that as an integral, and we're doing that as an integral. So the differential form is a very nice way to have things written because everything's clearly labeled and it's really hard to forget anything. Everything's kind of spelled out for you. So here we have the integral with respect, plus a constant of integration over here. Here we want the integral with respect to y of this, which would give me 2xy squared over 2, which plus a constant of integration, which is really just these twos divide out, xy squared plus a constant of integration. Okay? So now let's take the union of these, and that gives us our potential function. So f of x comma y is given by, well, the union of these is this one over here, right? Because this is already contained in here, but this one has something this one doesn't. So the union of these two sets is going to be xy squared plus x to the third over 3 plus a constant of integration. So there's our potential function. If ever you're not sure, you can always check this. If you take the partial with respect to x of this, well, that would be y squared plus, bring your 3 down, that would be x squared. So y squared plus x squared is the derivative with respect to x. Oh yeah, there it is, y squared plus x squared. If I want the derivative with respect to y, well, these don't have y, so they disappear. And the derivative of this with respect to y would be 2xy. Oh yeah, there it is. So if ever you're not sure you did that correctly, take the derivative with respect to x of the potential function, and it should give you your m. If you take the derivative of the potential function with respect to y, it should give you your n. All right, so now we're just about done. That means that our integral over c of x squared plus y squared dx plus 2xy dy is going to equal to, we're going to take our potential function, which was xy squared plus x to the third over 3. Here I'd like to put this constant of integration, but just like in Cal 1, the constant of integration will cancel out. Here I will write plus c just so that you can see it cancel out. So here is your integral, And by our theorem, we can take that by taking the potential function and evaluating it at the endpoints of my parameterization, where here my parameterization is from 0 to 2. Now keep in mind here this is t is equal to 0 to t is equal to 2. Here our function depends on variables x and y, but that's not difficult. Let's just take the lowest bound of t and figure out what x and y it gives me. Let's take the highest value of t and figure out what x and y that gives me. So here note that that means that x comma y is bound by, well, let's see here. That's, if you plug in 0 here, that's 0, 0. Oh, that's a terrible way to write that. Your vectors aren't bounded. The constant numbers within the vectors are bounded. So here, let me write this way. Here, I know my x is going to start from, okay, that's 0 if I plug that in. And if I plug this upper bound in, that's going to be 2 to the third, which is 8. And likewise here, t is 0 here. Okay, so then my y value is going to bound from 0 up to t squared, which is 4. So here, that's my x value. Okay, so it's going to go from 0, where t is equal to 0 to t is equal to 2. When t is equal to 0, I get 0. When t is equal to 2, that's 2 to the third power, which is 8. If this is y, if I plug in 0, that starts at 0. If I plug in 2, that goes up to 4. So here, this is going to go from the point 0, 0 up to the point 8, comma 4. All right. So here, my boundaries are going to go from 0, 0 up to 8, 4. All right. Notice that our value of t is bound by a single number. But here, when we integrate, we're finding a potential function. That's with respect to two variables, not an initial parameterization, but that's simple enough to convert. We know what t is. We know how t affects x and y. So take the bounds of t and turn them into bounds of x and y. Okay, when t is equal to 0, I have the point 0, 0. When t is equal to 2, I have the point 8, comma 4. So from 0, 0 to 8, 4. And I would just plug all that in. Let's see here. If I plug in 0, 0, well, let me start with this one. If I plug in 8, comma 4, that's going to be 8 times 4 squared plus 8 to the third over 3 plus a constant minus, and now I plug in 0 here, that's going to be 0 times 0 squared plus 0 to the third over 3 plus a constant. And notice that no matter what the constant is, it always goes away. So here, just like with the fundamental theorem of calculus in Calculus 1, here we generally don't write a constant. It's not necessary for a definite integral. All right? So here, we're really just focused on this part. Obviously, that's just 0, so we don't worry about that. And so our result will be, let's see here, 16 times 8 is 128 plus, oh, let's see, 8 to the third, that's 512 over 3. And so that's going to be, oh, let's see, actually I can divide that by 3, can't I? Oh, no, wait, I can't. That's a power of 2. So that's, let me just give these a common denominator. If I take 128 times 3, that'll give me 384. So that's going to be 384 over 3 plus 512 over 3, which is, let's see, 6, 9, 5, 6, 7, 8, 896 over 3. Just like that. Note that our parameterization didn't really matter. We never actually cared about using these as a substitution. We didn't care about, oh, exactly what is this parameterization. We never plugged anything in like that. We never said x is equal to this and y is equal to this. All that mattered was, okay, where does this start? Okay, my first point is 0, 0. Where does it end? My last point is 8, comma 4. 0, 0, 8, 4. And beyond that, everything is dependent on just what's your potential function and what are your endpoints. And that gives us our result. let's take a look at another example. Note we do have to check to make sure that our function, that our vector field has a potential function, meaning we do have to make sure that it's conservative. That'll be a big mistake in a lot of these sections. People will use the fundamental theorem of line integrals when it should not be used. This can only be used if your vector field is conservative. If your vector field is not conservative, you have to use the parameterizations as we did in 15.2. Right? So here, let's take a look at another example. Let's go ahead and evaluate the line integral over the contour C of f dot dr. So here they don't give it to us in differential form. Here they just tell us, okay, now f at x comma y comma z, so this is a vector field in 3 variables, is given by the vector y sine of z, x sine of z, and xy cosine of z. Okay. And we're given a parameterization. We're told that C is given by R of t, which is I thought I'd misread that. It's t squared comma 0. Third component 0. And our value of t is between 0 and 2. All right, so first of all, if this is a conservative vector field, awesome, things will be a lot simpler. If it's not a conservative vector field, we're actually going to have to go through and substitute in, okay, our x will be t squared, our y is t squared, our z is 0. We're going to have to substitute everything out, and then we're going to integrate from 0 to 2 of that times the derivative of this. All right, so first, let's check to see if it's conservative, because if it is, that'll save us a bit of time. If it's not, well, we got to do it the long way. All right, so with a function of 3 variables, the way we check to see if it's conservative is to find the curl. So conservative, if and only if the curl of f is equal to the 0 vector. All right, so remember the curl of f is given by the differential operator cross f, and we want that to equal to the 0 vector. So let's go ahead and do that. We're going to take the cross product, so let's write that I, j, k, I, j, k. Now, my differential operator is simply made up of the partials with respect to x, with respect to y, and with respect to z, in that order. And then I'll just write that again. And then f is made up of these vectors. So that'll be, or of this vector. Y sine of z, x sine of z, and xy cosine of z. And then again, y sine of z, x sine of z, and xy cosine of z. Okay, so now let's go ahead and multiply that out. Let's go ahead and find a cross product. That's going to be the derivative of this with respect to y. Oh, that's just going to be x cosine of z. That's going to be our first component. This one will be the derivative of this with respect to z. So the derivative of y sine of z is now y cosine of z. That's our second component. And then our third component is the derivative of this with respect to x, which is just the sine of z. All right, sine of z is a constant times x, so the derivative is just the constant. So sine of z, k. And then from that, we're going to go ahead and subtract our other vector. Let's go backwards here. The derivative of this with respect to z, well, that's going to be x sine of z, so the derivative is x cosine of z. Well, so far so good. That is 0. Let's see the next one. our curl should multiply out to be the 0 vector. Let's continue to see what happens. With respect to x, that's the only variable, that's a constant, and the derivative of x times a constant is just the constant. So that'll be plus y cosine of z j. And finally, this derivative here, the derivative of y sine of z with respect to y is just sine of z. So plus sine of z k. And sure enough, that's 0. This one minus this one is 0. This one minus this one is also 0. And this one minus this one is equal to 0 as well. Okay, so this is conservative. The curl of f is the 0 vector, so f is conservative, which means I can find the potential function and use the fundamental theorem of line integrals. Once again, if this was not true, then I would not be able to do this. Okay? If this was anything other than 0, I'd have to go back to section 15.2 and do it that way. All right, so let's go ahead and do this. Find the potential function. That's going to be the integral with respect to the first variable of the first component. That's y sine of z. I'm going to take the integral with respect to the second variable of the second component, which is x sine of z. And I'm going to take the integral with respect to the third variable of the third component, which is xy cosine of z. Oops, cosine of z, like that. So here, well, that's a constant with respect to x. And the antiderivative of a constant with respect to x is that constant times x, plus a constant of integration. Here, this is a constant with respect to y, and the integral with respect to y of this constant is this constant times y. And finally here, this is a constant times the cosine of z, so the antiderivative will be that constant times the sine of z. Plus a constant of integration. And here, the union of these three is my potential function. Notice they're identical, so my potential function really is just xy sine of z plus a constant. Okay, so now we're just about done. We have our potential function. So now we just need to find our initial and our final points here. Note here, when t is equal to 0, we get that we're at the point 0, 0, 0. Meanwhile, if we are at t is equal to 2, we get the point 4, 4, 0. 4, 4, 0. Just like that. And now we're going to go ahead and evaluate our integral by simply taking our potential function and evaluating it at those endpoints. So here that means that the line integral over c of f dot dr is going to equal to xy sine of z. I can leave the constant off. It would cancel out anyway. And this will be bound from the origin 0, 0, 0 up to 4, 4, 0. Here, if I plug in 4 times 4 is 16 times the sine of 0, well, that's going to be 0. So 4 times 4 times 0 is 0. Here, 0, 0, 0, well, that's going to be 0 also. And here, somewhat anticlimactically, our result is 0. It turns out that our line integral is just going to be 0. Now, this seems great, and it really is. It's a massive time saver. Now, you might think, well, okay, this works really, really well, assuming that my function is, or rather, assuming my vector field is conservative, meaning I can find a potential function. Is that the only time it works, or can I rely on it other times? It turns out that's the only time. So here's another theorem. Let's begin with a region R that is open and connected. Let R be an open connected region. Okay, we're going to take a vector field that is continuous on this region. Let F be a vector field continuous on R. Okay. Then it turns out that the line integral over C of F dot dr is line independent. Line independent. Let's use the term that this book uses. In fact, it's a very common term. Most books use it. Is path independent. Here, let's write that out nicely. Is path independent. If and only if F is conservative. So it's only going to be true in the case of a conservative vector field. Okay. The proof of this is, well, half of it's already done for us. That was the fundamental theorem of line integrals. So remember, if and only if means both directions are true. So here, if F is conservative, then it is, then, let me not use the word it, then the integral over C of F dot dr is independent of path. Independent of path by the fundamental theorem of line integrals. So that's half our proof already, right? If F is conservative, then I know that this integral is independent of path. So now let's prove the other direction. If this line integral is independent of path, let's show that that must imply that F is conservative. All right? So because it's independent of path, we can pick different paths to the same, between 2 points, and this integral should be the same either way. So let's define a function. F of x comma y to be equal to the line integral over C. Oh, well, that's bad grammar. If this, we can define a function. So here, let's leave this off to the end. So we can define a function, f of x equals to the integral of over C of f dot dr, which is the same as saying the integral of m dx. We can write it in differential form, plus n dy over C. We can define this function as this for C from x naught comma y naught, which is going to be a fixed point, to a point x comma y. Or in other words, okay, I have some open region. After all, that was our initial condition. We have an open connected region. So no fair having regions that are disconnected, no fair having regions that are closed. We want something that is open. So something, for example, like this. Okay. Now, we're going to pick a fixed point in this region. Let's just say right here, x naught comma y naught. And now we're going to define a function as being, okay, you want f of x, y? Okay, then start from here, go to your x, y, and find the line integral. Now, we began by assuming that our line integral is path independent. In fact, maybe that's where I should start. That's what I should have been my opening statement here. Assume the integral over c of f dot dr is path independent. Okay, so here, it doesn't matter what path I choose from here to here. If I take the line integral from here to here along any path, that answer will give me f of x comma y. Okay, so now let me be creative about what path I'm going to choose. I'm going to choose the following path. I'm going to pick a point that is directly horizontal from this point here. All right? I'm going to pick a point where my y value is exactly the same here and here, so I'll label that as something comma y, but my x value will be different. I've already used x sub 0, so I'll call that one x sub 1. Okay? Now here, I know I'm guaranteed to be able to find a point like that because, again, we have an open region, which means there are no isolated points and there are no points which are on the boundary, which means no matter what point I have some other point that is not that point nearby that is also in my region. Okay? So now, I can connect from here to here and from here to here. And that's the path I want to choose to go from here to here. All right. Here, this is piecewise smooth. So I'll call that part C1 and I'll call that part C2. Okay. So then the integral over C of f dot dr is really equal to the integral over C1 of f dot dr plus the integral over C2. I've just split this into two separate pieces, so I just add them both together, and that would give me the whole thing. Just like that. But since we have this written in differential form, we can also write this as our f of x comma y is equal to, well, that's going to be the integral over c of m dx plus n dy, which is equal to the integral over c1 of m dx plus n dy, plus the integral over c2 of m dx plus n dy. And all I'm doing is I'm writing these in their differential forms. Okay? So now let's take a partial of this with respect to x. After all, that's a function. It's a function of x and y. So I should be able to find a partial of it with respect to x. So now consider, we're going to take f sub x of x comma y. Okay, well, what is that? Well, notice this first integral is over c1. Here, this line is not dependent on this value of x. That is to say, the x that goes into my function. It still travels left and right, but it's not dependent on this value of x. So here, it is dependent on this value of y, because notice that y is the same as that y, right? But it's not dependent on this x. This x1 could have been anything. It could have been over here, over here, over here, anywhere. So it's independent of that result of x. So here, this does not depend on x at all. And because it doesn't depend on x, it's a function of just y. So here I want to call it f of just y, but since I'm using f for something else, let me call this g of y. Okay, so this is g of y, and now I'm going to take its derivative with respect to x. All right, so that's going to be g sub x of y. Plus, here I'm going to take the derivative with respect to x. And here maybe I shouldn't mix my notations. Here let me write them all in terms of del x. So here I want to take the derivative with respect to x of this. So del x of f. That's going to be del x of g of y. Because after all, this right here is just a function of y. It's not dependent on this x. Right? This x1 could have been anything. But it is dependent on y, because those are the same y. So here, that's a function of just y. Now over here, I'm going to take the derivative with respect to x of this one. Notice on this one, delta y is 0 because I never go up or down. Y is already exactly what it needs to be to go from here to here. It would just go across only depending on the variable x. So here this would be the integral over c2 of m dx. And here dy is just going to be 0 because here you're traveling straight across. There is no change in y. Right? You're only traveling horizontally. So here you can write this as the integral of c squared m dx plus 0. So here we don't bother writing that. Okay, so then that means that, well, let's see here. That's del x of f of x comma y. That's a function of y only. Doesn't depend on x. So if I take its derivative with respect to x, that's just 0. Here, that's the derivative with respect to x of an integral with respect to x. Right here, that's integrating with respect to just x. So the derivative of the antiderivative, well, that's the fundamental theorem of calculus. The derivative of the antiderivative of m would just give me m. Okay. Now we can do the same thing for a different path. Note, if I choose this path over here, I can do something similar. Instead of taking a path that puts me right next to my point that's desired, I can get a different path that puts me right underneath the point that I desire. So let me call this one C3 and C4. Okay. So here we follow the same line of thought. We can write this as f of x comma y is equal to the integral, I'm going to start from right here, is equal to the integral over c of m dx plus n dy, which is really equal to the integral of over c3 of m dx plus n dy plus the integral over c4. If I add these two, that'll get me right to where I need to go. So c3 plus c4 of m dx plus n dy. But just like in our previous derivation here, this second contour, this c2, we only move horizontally, which means there was no change in the y direction, so this was 0. Well, for this one, c4 moves only straight up and down, which means there is no change in the x direction. So right here, c4, m dx plus n dy, this is going to be 0. You don't move along the x direction here. You're going straight up and down only. Here, this is a function that doesn't depend on that y value. Because after all, even though this point is directly underneath here, so it uses the same x, right? That x has got to be the same as that x. Here, the y values are different. So I can call that one y1 and y. So here, this y1 doesn't have to be that one that point in particular. I could have stopped down here and gone straight up, or down here and gone straight up, or really close up here and gone straight up. Here, it doesn't depend on that value of y. So here, this function this function over c3 doesn't depend on y. It's only a function of x. So here, I can take all of this and just call it, I've already used f and g for something. Let me call this h of x. All right? Plus, and this is the integral over c4 of n dy. Okay, so then that means that if I want to take the partial of f with respect to y, I did it with respect to x in the previous part. Here, let me take it with respect to y. Well, that's going to equal to the partial with respect to y of f of x plus the partial with respect to y of this expression. Notice that's a function of x, so if you take its derivative with respect to y, that's just going to be 0. Okay, so that's going to equal to 0. Plus, here, this is the derivative with respect to y of the integral with respect to y of n. Oh, that's just going to give you n. So here, we have a function, f of x, which if I take its derivative with respect to x, I get m. And if I take its derivative with respect to y, I get n. So that means del x of f of x comma y, comma del y of f of x comma y. If I turn that into a vector, I say, okay, that del x of f of x comma y, that's m. And that del y of f of x comma y, that's just n. Or in other words, well, look, this is the partial with respect to x of a function, comma, the partial with respect to y of a function. That's called the gradient. If you think back to chapter 13, that's the definition of the gradient of f. Okay, so we have the gradient of f is equal to, well, m comma n, that's how we were writing our vector field. So here we have found a function whose gradient is our vector field. Oh, but by definition, that means that vector field is conservative, because that's what it means to be conservative. You have some function whose gradient gives you your vector field. Thus, f is conservative. Okay, so we've proven both directions. If you have a conservative vector field, then it's path independent. If you have something that's path independent, then you have a conservative vector field. So it's true in both directions. And that concludes our proof. All right. We can summarize, we've had a few definitions and a few theorems in this section. We can actually summarize all of that with one last theorem. Here we're not going to prove this because it's already been proven. This theorem is simply the compilation of all of our current definitions and theorems with regards to conservative vector fields. Theorem. Here, this is expressed with respect to a vector field of 3 components, but note it's the same for a vector field of 2 components, or should you need one, something with 4, 5, or 6 components. Let's begin with a vector field. Let f of x comma y comma z be given by a vector, give a vector field whose components are m, n, and p respectively. Let's let that vector field have continuous first partial derivatives. I guess I should start with that. Let R be a open connected region, just like we had in the last theorem. Let R be an open connected region. And now let F be a vector field composed of 3 components, m, n, and p, where m, n, and p are, well, I guess I should say have continuous first partials in R. And finally, let's have a contour. Let's have a line here. Let C be piecewise smooth in R. Then all of the following are equivalent. Then all of the following are equivalent. Meaning if you have one of them, you have all 3 of them. If you don't have one of them, that means you don't have any of them. They're all identical. They're all interchangeable. If you have one, you have them all. But if you don't have one, well, then you don't have any of them. The first statement is F is conservative with potential function f. Okay. The second statement is that the line integral over C of f dot dr is path independent. And 3, that the line integral over C of f dot dr is equal to 0 for all closed curves C. For all closed curves C in R. Okay? Here, note all this one is saying is, okay, if you're independent of path, let's say you're trying to integrate something over this region here, starting from this point back to this point. Well, one thing you could do is you go out around this way. Another thing you could do is you go out and then come back. But another thing you do is just start there and never go anywhere. And that's also a perfectly valid path. So if you have a closed contour which brings you back to your starting point, then due to path independence, you could just say, well, here, I'm just not go anywhere. So if I'm taking the integral from A to A, just like in Cal 1, that's got to be 0. So if you take a line integral over a closed curve in a conservative vector field, then that's got to equal to 0. And that's the end of our section. Incidentally, we're not going to go into it because this is not formally a physics class, even though there's a lot of overlap given our context, our material. We have seen why we talk about conservative vector fields. They conserve our line integrals over paths. You're independent of path. But there's another reason why we talk about conservative vector fields. It is related to what we have been talking about. And there's also a reason why this is called a potential function. It has to do with potential and kinetic energy. One of the laws, one of Newton's laws is the conservation of momentum, right? Well, a related property is Faraday's conservation of energy formula. That's where a lot of this stuff originated from. This is called the potential function because it's the function that gives you the potential energy of your vector field. It's conservative if you conserve kinetic and potential energy. So if you study university physics and you go into the calculus of potential and kinetic energy and conservation of energy and conservation of momentum, that's where you'll see all of this. So that highlights why we have these titles for them. For us, you can say, oh, it conserves our line integrals. But formally, the reason we use this was because we were talking about conservation of energy. And likewise, this is a potential function because the potential function is what defines the potential energy, which is conserved between, when you talk about conservation of energy, you talk about the conservation between potential and kinetic energy. Essentially, the sum of potential and kinetic energy must always be the same. All right? So that's something for another course, but it does highlight our language. Potential function is a function that gives you potential energy. In a conservative vector field, you conserve energy. Namely, the sum of potential and kinetic energy would always be the same. As an assignment for the section, you may want to try problems, let's see, 15.3. Go ahead and try 5 through 35 odd. One warning as you're trying these problems, remember that the fundamental theorem of line integrals depends on having a conservative vector function whose potential function you can find. Buried amongst these problems, you're going to have a couple of them where when you check to see if they're conservative, they're going to turn out not to be. In that case, what you need to do is you need to go back to section 15.2 and evaluate them as line integrals without the fundamental theorem, meaning you're going to use your parameterizations to convert f into a function of t. You're going to take the derivative of your parameterization of your vector, you're going to find the dot product, and then you're going to evaluate over the bounds of t. All right, so that would be from a to b of f of t dot dr dt dt. All right, so here, make sure you always check to see if it's conservative. If it is, great. Use the fundamental theorem of line integrals because it's so much simpler. If it's not, go back to 15.2 and do it that way. All right. If anybody has any questions, please make a note of them and reach out to me. And I hope everyone has a nice day.